want to speak about the fractional calculus. Some first words about the presentation of this field. Fractional calculus has a long history, about 200 years. It was introduced at the beginning of the 19th century by Liouville, Riemann, Abel. These outstanding mathematicians understood that it is possible to introduce some ideas like fractional integral, fractional derivatives, and fractional equations involving fractional derivatives. But I can say that for a long period it was neglected by the majority of mathematicians. And the first book on fractional calculus appeared in 74, Oldham and Spanier. It was not really a book, a mathematical book. It was a sort of collection of practical results. There were long lists of fractional derivatives, of elementary functions, and some basic ideas. The first book, very important book, was published in Russia in 87 by three mathematicians, Samko, Marichev, and Kibas. And they produced a very big book which was translated in 93 in English. And it is a book of about 1,000 pages with a huge list of references, 80 pages of references. You can, if you look at this book, find all that was published over 150 years in all countries of the world in this field. And the book was extremely expensive. When it was bought by my department, I had some problem because the cost was of $500. And afterwards I met one of the others, Kibas, told me, you are very good if you have sufficient money to buy such a book. And unfortunately, the three people who wrote this book left Russia. One is now in Portugal, the other one has completely disregarded mathematics, and the third one unfortunately died in an accident in the Caucasus. So I consider this as a reference book, a book by Samko, Kibas, and Marichev. For elementary fractional calculus, you can look at the book of Probabilistic, which appeared in 99. Afterwards, a lot of papers, a lot of books were published. And from my point of view, also from the point of view of probability, I say that starting from the end of the 90s, the number of papers involving fractional calculus increased enormously. And all areas of probability have been influenced by these ideas. So what I want to do is to present the basic ideas of fractional calculus following the historical development of this subject. And then I will present some applications to various fields, in particular to fractional diffusion equations, telegraph equations, and some other point processes involving fractional calculus. This is the program of my lectures. So I start from very elementary things, that is the fractional integral and the fractional derivative according to the Riemann-Liouville approach. By the way, I am not sure that I'm able to use this trick because I have the habit, maybe due to my frequent travels in Russia, to write on the blackboard. But if I'm not able, I will write on the blackboard and there. And I will write a few things and speak a lot in order to make all things clear. So the first result, first definition I want to introduce is the fractional integral according to the Riemann-Liouville approach. Oh, it doesn't work. First result I want to introduce is the Riemann-Liouville fractional integral. Usually in the courses of analysis, you start by introducing the derivative. In fractional calculus, you must first introduce the integral, the fractional integral. We use this notation. Alpha is the degree of the fractional integral, which is usually a positive number, and it must be written in this way: 1 over integral from 0 to x minus t, alpha minus 1, f of t. Gamma is, of course, the gamma function, and x is supposed to be a positive number. This is the so-called Riemann-Liouville fractional integral of order alpha. Alpha is a positive real number. Of course, there are more general definitions where alpha can be also a complex number. In the book of Samko, you can find such generalization. But for the introduction, I just speak about the case where the degree of the fractional integral is a positive number. And such an object has some properties. Linearity, that is, integral is equal to homogeneity, integral of order is equal to this, and above all, there is no, yes, the semi-group property that is the integral of alpha or the integral of beta f is equal to integral of alpha, integral of beta alpha, integral of alpha plus beta f. This is the semi-group property of the Riemann-Liouville integral. Now, the following problem arises. Why is this called fractional integral? Which is the reason to call this fractional integral? Intuitively, which is the inspiring idea of this definition? The idea is based on the so-called Cauchy formula, And the Cauchy formula must be written in this way. The integral of this is equal to 1 Liouville essentially had this idea. If you look at this formula, which is elementary, can be easily proved, this is x. You can replace this number by a gamma function,
f
f of x on it. You can replace the gamma function here and write instead of n an arbitrary positive number alpha. This suggests the idea that this can be, in a certain sense, interpreted as the integral of a fractional number of times of the function f. And you arrive at the formula E alpha of f of x, which I wrote before, gamma alpha integral from 0 to x minus t alpha f of t. This is the inspiring idea of the fractional calculus given by Liouville. I have here the details of the proofs of all the properties I have given, in particular of the semi-group property of the fractional integral and how this formula can be proved. Another type of fractional integral is the so-called Hadamard fractional integral. Maybe I can try to use slides. You have slides. Now I write the form of the Hadamard fractional integral. Equal to 1 over gamma alpha integral from 0 to x f epsilon y logarithm alpha minus 1 x over epsilon 0 to 1 f of t divided by t logarithm alpha minus 1 over t. As you can see, this is an alternative form which is based on the same ideas of the Riemann-Liouville integral. It has this structure, you have something involving the logarithm, and also this is based, it is inspired by a formula similar to that of the Cauchy formula. In particular, if you take this integral from 0 to x from 0 to x1 this also is a formula of the type of the Cauchy formula, and if you replace n minus 1 factorial by a gamma function, you arrive at the Hadamard fractional integral. It must be underlined that the Hadamard fractional integral is considered also in the book by Sanko, Ibas and Marichev, but there are very few papers involving this type of fractional integral and fractional derivative. So the basic ideas are essentially the so-called Riemann-Liouville integral and the Caputo integral. Recently, I also learned of the existence of other type of extensions of the integral, which are called the Erdelyi-Kober integrals. There are two types of definitions. M eta minus m alpha gamma of alpha integral from 0 to x m minus u m alpha minus 1 u m eta f of u d u of m. And the other definition of the Erdelyi-Kober integral is the formula E alpha m of f in the point x is equal to m divided by gamma of alpha integral from 0 to x m minus u m alpha minus 1 u m minus 1 f of u. Alpha is a positive number, m is usually a natural number. And if you look at this definition, when m is equal to 1, you retrieve the Riemann-Liouville fractional integral. So it is an extension which has been introduced independently in the 40s by Erdelyi and Kober. As I said at the beginning, the fractional integral is the basis for the introduction of the fractional derivative. The idea of constructing fractional derivative was first proposed by Leibniz in a letter which is considered as the starting point of fractional calculus. Leibniz, one of the two founders of differential calculus, had the idea, can we construct, for example, the derivative of order 1/2 of a function? He was not able to give an answer to this. And only UV was the first one who tried to introduce what is now called the fractional derivative according to Riemann-UV. And this was published in a paper dating back to 1832, 1833, 1831. In that period, he published a series of papers involving these ideas. So now I give you the explicit definition of fractional derivative according to Riemann-UV. Derivative of order alpha, for us, we consider alpha bigger than -1, is equal to the derivative of order m of the fractional integral of order n minus alpha for the function f in the point x. M and alpha are related in this way. Alpha is less than m, bigger than m minus 1. That is, the integral part of alpha is equal to m minus 1. So explicitly, you can write the fractional derivative of order alpha according to Riemann-UV in this way. Derivative of order m with respect to x of 1 divided by gamma m minus alpha, integral from 0 to x minus t, m minus alpha minus 1 f of t. So in a certain sense, you can see that the fractional derivative is an integral and is based on this definition. First of all, you make the fractional integral of order m minus alpha, and then you take the derivative of order m of this function. And the result is called Riemann-UV fractional derivative. Also, this has an intuitive basis. Otherwise, why to call an integral derivative? This contradicts the usual approach to these things. So the intuitive idea on which this definition is based was given by Liouville himself, who said, let us take the derivative of order m over power. Derivative of order n over power x m. Suppose that m is bigger than n. Of course, everybody knows that this is equal to gamma of m plus 1 divided by gamma m minus n plus 1 x to the power n minus n. Now everybody knows this. Then, as he did with the fractional integral, you replace the gamma function, which can be defined everywhere for all positive and negative numbers, even for complex numbers. You replace these gamma functions with gamma functions and root this derivative of order n of the function x of beta is equal to gamma beta plus 1 divided by gamma beta minus nu plus 1 x beta minus nu. This is the idea he suggested to give sense to the fractional derivative of an arbitrary order of a power function. Simply taking this formula and replacing gamma function and extending it to real numbers. Now, the idea is the definition we gave before, fractional derivative, produces the result or not? Yes, it is coherent with this intuitive idea. If you take the definition of fractional derivative for the power function, you obtain exactly this result. I mean that if I make the derivative fraction of x to the power beta, according to the definition, nu for us is between m minus 1 and m. Derivative of order m x m of the gamma function m minus nu, integral from 0 to x minus t, m minus nu minus 1 of t to the power beta. If you carry out this integral, this leads to the beta function, and then you perform the derivative with respect to x after some calculations which are here in my notes, you arrive at the result which was proposed by Lewis, gamma of beta plus 1, gamma beta minus nu plus 1, x beta minus 1. Of course, this gives rise to some strange facts. For example, the derivative of the constant is a function of x, which is rather strange. It was one of the points which rose skepticism towards fractional derivatives. But in any way, I must say that for the fractional derivatives, the following properties hold. The derivative of order alpha of the sum of two functions is equal to the derivative of alpha plus derivative of g. The derivative of a constant multiplied by f is equal to the constant derivative of f. Unfortunately, the derivative of alpha applied to the derivative of beta is different from the derivative of beta of the derivative of alpha of f. And it is also true that it is different from the derivative of alpha plus beta f. So it doesn't enjoy the semi-group property which we said is valid for the fractional integral. And you can see that this is not true by simply using a counterexample. 1/2. Alpha equal to 1/2 and beta equal to 3/2. Then you have that the derivative of order 1/2 x 1/2 is equal to gamma of 3/2. And this is equal to square root of 2 of p divided by 2. If you make the derivative of order 3/2 of x to the power 1/2, this is equal to 0. Essentially because you are applying this formula, derivative of alpha x to the power nu equal to gamma of nu plus 1 divided by gamma nu plus 1 minus alpha. And if nu is equal to 1/2, alpha is equal to 3/2, this is gamma of 0, which is clearly infinite. X nu minus alpha, this becomes in this case equal to 0. Then, if you make the derivative of order 1/2 of the derivative of order 3/2 of x to the power of 1/2, you have that this is equal to 0, because this is 0 and the derivative of order 1/2 of 0 is 0. On the contrary, if you make the derivative of order 3/2 of the derivative of order 1/2 of x 1/2, this is equal to the square root of p divided by 2 gamma minus 1/2 x minus 1/2. So this simple counterexample shows that the commutative property of the fractional derivative does not hold, and also the semigroup property of the fractional derivative does not hold. Now, some other properties concerning fractional and integral derivatives according to Riemann. By the way, according to the book of Sanko, Kibas and Marichev, it is clear in which papers Liouville introduced these ideas, but I'm not realized clearly in which paper, in which point of his production Riemann introduced these ideas. But I can say that some years before Liouville, Abel was able to solve a very important problem, autochronia problem, by means of fractional integrals. So in a certain sense, you can say that one of the founders of fractional calculus is Abel, Erich Abel. Now, combining fractional derivatives and fractional integrals, you have the following result. The derivative of order alpha of the integral of order alpha of the function f is equal to f. This is not true if you change the order of the two operations. The integral of the derivative is not equal to f. And we shall see afterwards because the reason because this is not true. But in order to show that the derivative of order alpha, of the integral of order alpha of the function f is equal to f, you simply consider the definition of fractional derivative. And you say that the fractional derivative of order alpha is equal to the derivative of order m of the fractional integral of order m minus alpha. And of e of alpha of f. Now, we know that the fractional integral has the semigroup property. So this is equal to the integral of the sum of the orders. this is equal to the derivative of m of the integral of order f of the function f. And it is clear that this is equal to f. If the derivative, the order of the derivative and the order of the integral are different, you have the following result. The derivative of order alpha of the integral of order beta can be written as integral of order beta minus alpha if beta is bigger than alpha, and becomes the derivative of alpha minus beta in the other case. So I just show you what happens in the case where beta is greater than alpha, greater than 0. If you take the derivative of order alpha of the integral of order beta of the function f, you consider that beta is bigger than alpha, and then you use the symmetry property of the fractional integral, and you have derivative of alpha of the integral of order alpha, integral of order beta minus alpha of f. Then this gives rise to integral of order beta minus alpha of f. And this is the first case. First case when beta is bigger than alpha. In the other case, when alpha is bigger than beta, is when alpha is bigger than beta, bigger than 0, we must consider that alpha is in the interval m minus 1, m, and alpha minus beta, alpha is bigger than beta, is between n and n minus 1. Then, in this case, you can write the derivative of order alpha of the integral of order beta of the function f equal to, you simply write the derivative as derivative of order m of the integral of order m minus alpha of the integral of beta f. Then you write using this further decomposition and taking into account that the integral, fractional integral enjoys the semi-group property, you can rewrite this as derivative of order m minus n integral of order m minus n derivative of order n of the integral of order n plus beta minus alpha of f. And this, of course, is equal to the identity operator, and this is equal to the derivative of order, this was alpha of alpha minus beta of a function f. So as you can see, applying firstly the integral and then the derivative, when the order of the two operations is equal, you recover the function. When the two orders are different, you can arrive at the fractional integral or to the fractional derivatives. Instead, problem is that if you start with the integral of the derivative, integral of order alpha of the derivative of order alpha of a function f, you obtain f sum j from 1 to k, derivative of order alpha minus j of f in the point x, where x is equal to 0, multiplied by x alpha minus j divided by gamma alpha minus j plus 1. Of course, k is bigger than alpha, and alpha is bigger than k minus 1. So the inversion of the two operations gives rise to a result which is completely different from what happens in the usual calculus, because you have in this case f minus something which is related to the initial conditions at point x equal to 0. I have here the proof of this fact. I don't give the details because I have not sufficient space to write on. And at this point, I often had people asking me which is the relationship between fractional derivatives and the usual idea of derivative as the limit of a fractional increment. And the idea was in a certain sense suggested by the Marchot fractional integral. Marchot fractional derivative. I have seen that the paper where Marchot introduced this remark was published in 1924-25. And the idea is that you can take the Riemann-Liouville fractional derivative, make some manipulations, and you arrive at this result. The derivative of order alpha of the function f in the point x is equal to, say, for example, alpha in the interval 0, 1, in order to make very rapidly the result. This is equal to the derivative of order 1. You have f of t divided by x minus t to the power dt. Then there is a gamma 1 minus alpha here. And if you make some manipulation, you arrive at the following formula. F of x divided by x to the power alpha, gamma 1 minus alpha plus alpha divided by gamma 1 minus alpha, integral from 0 to x, f of x minus f x minus y divided by y 1 to the power 1 plus alpha dy. And you see that in the Marchot fractional derivative, you have these incremental ratios, but integrated from 0 to x. And what is very interesting is that you have this quantity, which is well known for the specialists of Bernstein functions or Levi processes, and it is a Levi measure which appears everywhere in the study of Poisson processes and Levi processes and things like that. So in a certain sense, you must weight the ratio with something which is related to the Levi measure. Now, I must say that another important fractional derivative is related to the Riesz potential. Riesz Marcel-Ritz potential. It is written in a certain sense as an integral which is inspired by the Riemann-Liouville fractional integral. Integral of order alpha of the function f in the point x is equal to 1 divided by 2 gamma of alpha cos alpha p divided by 2 integral from minus infinite to plus infinite x minus t to the power alpha minus 1 f of t, which can be written also, take this big constant again, and you divide the integral from minus infinite to x plus minus 1 to the power m minus 1 integral from x to infinite. And in each term you have something similar to the Riemann-Liouville integral. The only difference is that the function f is defined on the whole real line, and the first part is the integral from minus infinite to x, and the second part is from x to infinite. These are called the Weil fractional integrals. Weil fractional integrals. Fractional integrals. So combining them suitably, you arrive at the Ritz potential. And this constant here in front of the integral is due to the, the necessity to give to the Fourier transform with respect to x of this of the derivative, the Ritz derivative, a suitable form. So this is not strange, but is due to the fact that we want to evaluate the Fourier transform of the Ritz fractional derivative and obtain something which is very important from our point of view. I must say that the Ritz potential has some properties which are similar to those of the Riemann-Liouville integral, but only for specific values of the involved orders. For example, if alpha is in the interval from 0 to 1, beta is in 0 to 1, alpha plus beta is from 0 to 1, then you have the semigroup property also for the Ritz potential. That is, E beta or E alpha of f is equal to E alpha E beta of f equal to E alpha plus beta of f. But only when alpha is in 0, 1, beta is in 0, 1, alpha plus beta is in 0, 1. Otherwise, the integrals defining the fractional Ritz potential do not converge, and so this property is not valid, does not hold. Based on the, by the way, I have here the proof of the semigroup property of the Ritz potential. To give all details, it takes about 1 hour at least, with a big blackboard available. So I just arrive at the Ritz fractional derivative. Fractional derivative can be written in this way. Usually it is written with this symbol. Derivative of order alpha of a function f according to Ritz is equal to minus 1 divided by gamma m minus alpha, derivative of order m
xm divided by 2 cos alpha p divided by 2, integral from minus infinite to plus infinite f of t divided by x minus t alpha plus 1 minus m dt. That is, you can repeat the structure of the Riemann-Liouville integral and write derivative according to this of a function f, alpha we suppose to be a positive number, is equal to the derivative of order m of the Ritz potential of order m minus alpha of f. Instead of having the Riemann-Liouville integral, here you have the Ritz potential. So the structure is exactly the same. And as I said before, the reason for this constant in front of the derivative and in front of the integral is due to the fact that if you take the Fourier transform E gamma of x of the fractional derivative of order alpha of the function f of x is equal to gamma to the power alpha of the fractional Fourier transform of f. So this is very important for us. This gamma to the power alpha absolute value. And also for this, I have the explicit proof when alpha is in 0, 1, but it is easy to show that this holds also for alpha in 1 to 2 and for all values or positive values of alpha. I forgot to say minus here. There is also the Hadamard fractional derivative, which, as I said before, is not so popular among specialists of the fractional calculus. The most important fractional derivative from those who study fractional equations is the Caputo fractional derivative, which is defined in this way. Fractional Caputo integral. Caputo derivative and integral, but derivative for us is important in this moment. Jerbashan introduced this derivative in the 60s. If you look at the book by Samko, Marichev, and Kibas, you will find a long list of references where there are results by Jerbashan himself, Jerbashan and his pupils, Jerbashan and the other colleagues, and Caputo, which was a professor of our university, was a specialist of earthquakes, of geophysics, and introduced this fractional derivative in a book written in Italian, Elasticità e dissipazione, something of this type. He gave me as a present his book, published some years later. And the derivative of Caputo is given by the following formula. Derivative of order alpha of the function f is equal to 1 divided by gamma m minus alpha, integral from 0 to x, f derivative of order m of f, m of t divided by x minus t alpha plus 1 minus m. That is, the definition is integral of order m minus alpha of the derivative of order m. So the difference with respect to the Riemann-Liouville fractional derivative is that you have firstly the derivative inside the integral, and then the fractional integral of order m minus alpha. So they interchange the order of the operation. I'm practically sure that mathematicians of the caliber of Riemann and Liouville understood which are the drawbacks of their definitions and also of the possibility of interchanging these operations. For example, those who suppose that the Gerbachev-Caputo derivatives are more suitable for the study of fractional differential equations is that you need integer values initial conditions for these equations, while if you study fractional equations where you have the Riemann-Liouville derivative, you need initial conditions which are themselves fractional derivatives. And this is not very easy to justify. For example, for a constant, the fractional Gerbachev-Caputo derivative is equal to 0, while in the other case is a function of x, which is in a certain sense a paradox. But this has appeared only very recently, relatively recently, because it was published, as I said, in the 60s, not before. I must say that another derivative which usually is not used by specialists of fractional equations is the so-called Grünwald-Letnikov fractional derivative. Grünwald-Letnikov fractional derivative, and is based on this idea. Intuitively, if you take the usual derivative of a function f in the point x, this is the limit of the incremental ratio f of x divided by h, and then you take the limit. The derivative of order 2 is equal to the limit of f x plus 2h minus 2f x plus minus plus f, like this. It can be written in different form, but x plus h divided by 2 over h to the square when h goes to 0. And the derivative of order n can be written as the limit when h goes to 0, or the sum from 0 to n minus 1 to the m n over m f x plus n minus m h divided by h to the power n. And the idea of Grünwald-Letnikov, it was in the 60s of the 19th century, was simply to replace n with alpha in both members and define fractional derivative order alpha in this way. fractional derivative of order alpha. X is equal to lim, when h goes to 0, 1 divided by h to the power alpha, sum from m from 0 to infinity. This is the first difference. Alpha to the power m f x plus alpha minus m h. This is simply an operation which has the same form of that was made by Liouville with the derivative of order alpha for the power of a function x. So I have here a presentation of the fractional integrals and fractional derivatives which usually are treated in the historical books of fractional calculus. There are other derivatives and other integrals which appeared recently. Hilfert derivative, Hilfert fractional integral, which are more and more complicated but not so extensively used in the applications. From my point of view, the two prevailing definitions are those of Riemann-Liouville and Gerbacian-Caputo. From the point of view of probability also, the Riesz potential and the Riesz fractional derivative are also very, very important. Above all, when we treat the governing equations of the stable processes. Now, I don't know how much time I still have.
You want to stop for 5 minutes, 10 minutes?
Oh, break?
Yes, break.
Yes,
And
a
then
small
we
break.
start,
Okay.
So we will start on 12 and 15. Just 10 minutes until 1 o'clock.
Ora vediamo se riusciamo a tornare a lavagna, se no, se tu mi dai questi fogli, alcuni fogli anche scritti a mano, io li scannerizzo, mi mando il PDF e li proiettiamo.
Perché quello non funziona.
No, perché basta che tu mi dai i fogli scritti a mano, perché io li posso scannerizzare.
Intanto ti do quelli
che tu hai fatto fino adesso, in modo tale quindi che io posso...
Sì. Ecco, quelli non li uso più. Poi ho saltato tutte le dimostrazioni perché non è possibile scrivere.
E perciò, quindi invece se tu me li dai così, allora per domani, quando è ora per dopodomani? Quando sai la lezione? Domani. Se ce li hai già scritti a mano,
tutto scritto.
E dopo me li dai e io li preparo, li scannerizzo. Io posso fare pure a casa, perché a casa si può stare, ma lo faccio qua.
17, 18, ecco, questo qua è tutto quello che io ho fatto. Naturalmente ho fatto molto, ma molto di meno di quello che ho scritto.
Sì, vabbè, ma tanto poi loro se lo vogliono, a parte che li hai preso, però questi li posso passare. Scrivimi ragazzi. After that will be the lunch in this room on my right, and we start at 2 p.m.
I want to write to this record the main definitions I introduced so far, in order that you can look at them constantly. here you have the fractional integral and the fractional derivative according to Riemann-Liouville. According to Caputo, Caputo. Now I give some other technical results concerning these fractional derivatives. For us it is very important to be able to evaluate the Laplace transforms and the Fourier transforms of the fractional derivatives. In particular, we give the Laplace transforms of the Riemann-Liouville fractional derivative and of the Caputo fractional derivative. It is well known that the Laplace transform of the nth order derivative of a function in the point S is equal to, I give explicitly, e to the power st derivative of order n of a function f is equal to s to the power n Laplace transform of f minus sum from k from 0 to n minus 1 s to the power k derivative of order n minus 1 minus k with respect to x to the power n minus 1 minus k of the function f of x in x equal to 0. What happens if instead of the nth order derivative we have a fractional order derivative for the Laplace transform? What changes? I give you the two results in the case where we take into account the fractional derivative, fractional Riemann-Liouville derivative. The Laplace transform of the fractional derivative of order alpha of the function f in the point S is equal to s to the power alpha, Laplace transform of f in the point S, of course, minus sum from k equal to 0 to m minus 1 s to the power k derivative of order alpha minus 1 minus k of f in the point x equal to 0. So compare these two formulas. The first part is simply the replacement of n with alpha, and the second part is the replacement of the derivative with the fractional derivative in the point x equal to 0. This is simply the reason for which in the fractional differential equations involving the time fractional derivative, you need that the initial conditions must be expressed in terms of fractional initial conditions. This is a drawback of the Riemann-Liouville derivative. while for the Caputo fractional derivative, you have instead the following result. That the fractional derivative of order alpha of the function f in the point x is equal to s to the power alpha, Laplace transform of f minus sum from k to 0 to m minus 1, s to the power alpha minus 1 minus k, derivative of order k, dtk of f in the point t equals 0. With respect to the previous formula, here you have s to the power alpha minus 1 minus k, and the initial conditions are written as integral order derivatives. This is the basic difference between the Riemann-Liouville and the Caputo derivatives. Of course, as I said before, we need also to know the fractional derivatives, the Fourier transforms of the Riemann-Liouville and of the Ritz fractional derivative, but I have given before the result for the Ritz fractional derivative, and I don't want to repeat it because I'm not able to give the details of the proofs, which take a lot of time and a lot of space. I must say something about the fractional calculus and my contact with this branch of mathematics. I must say that I completely ignored the fractional calculus till the 90s. I've never heard about fractional calculus, and I have never seen papers in probability. My specialty is probability concerning fractional derivatives. And once I remember that during one of my numerous trips in Russia, I met a person who suggested me to study wave equations with some derivatives of order 3/2. I thought that it was a joke, because it seemed to me that it was impossible to have non-integer derivatives. And since in Russia there are many people who drink a lot, I thought that he was drunk hard. And when I returned back from Kazan, this happened in Kazan, the native place of Lobachevsky, I told to my colleagues, you know, in Russia there are people who use fractional derivatives, and nobody around me listened about the existence of this. Only at the end of the 90s, I have seen a paper concerning the diffusion equation of fractional order with initial conditions which are the form of a stochastic process. So I started getting interested in this field of mathematics, and I discovered the whole world, which I completely ignored. And I invited people to tell me what is this fractional calculus. In particular, I remember that I invited Mainardi, who was a pupil of Caputo. Caputo started writing things about this in the 60s. And then I invited Kilbas. In 2002, he came to our department in Rome and delivered a talk. And he told me that he was preparing a new book, which was published in 2006 with Trujillo. So I understood that this is a serious field of mathematics, And I immediately understood that many things can be done using fractional calculus within probability and stochastic processes. This is it is in a certain sense stupid to meet people who give you this idea and to disregard it as the result of a drunkard who doesn't speak seriously. By the way, I thought that the person who told me about the existence of fractional calculus was not drunk at all. He was a serious person who made serious mathematics. So it was my fault that I was not able to catch this idea some years before than I did. And the reason for which I was interested in fractional calculus is that you have in probability, it is very popular, diffusion processes. Diffusion processes play a central role in probability stochastic processes, and all that is related to Brownian motion, diffusion equations, and things like that have become extremely popular. So the idea that it is possible to extend these basic facts using fractional calculus has become important, and this is the reason for which I want to tell you what has been done using the ideas I presented so far. So the first and the simplest equation, fractional equation, is the diffusion, the time fractional diffusion equation. Time fractional diffusion equation. And I can write it in this form. Derivative of order nu of nu equal to lambda square derivative with respect to space. X is supposed to be a real number, t positive number, lambda square plays the same role of the velocity in the wave equations. This object was studied, as far as I know, by some physicists in the middle of the 80s. Weiss. I usually refer to a paper by Weiss of 86. And the derivative appearing here, according to his assumption, was the Gerbacian-Caputo fractional derivative. So here appears the fractional, which is written on the blackboard, and U, of course, is a function which must be twice differential with respect to x, and since nu must vary in this interval, including 2, we suppose that it also has continuous derivatives up to order nu. Why nu must be less than 2? The reason for which that nu must be less than 2 is that we want to produce positive valued solutions of this equation. But in principle, you can study these equations also when nu is bigger than 2. And this has been done in other areas of mathematics or something related to probability and leading to the so-called pseudo-processes. It is clear that this equation, when nu is equal to 2, coincides with the wave equation, the equation of the vibrating string. When nu is equal to 1, it is the heat equation. So when nu varies in this interval, you have generalizations of the heat and the wave equation. And these basic equations of mathematical physics are special cases of the time fractional diffusion equation. So this must be said, first of all. Of course, we can introduce here the fractional derivative. For example, the fractional derivative in the sense of wreath, and you arrive to the time fractional space diffusion equation. Fractional derivative with respect to time and lambda square, fractional derivative, say alpha, here in the sense of wreath. This is the wreath fractional derivative, and this is the Caputo fractional derivative. The wreath derivative. The reason of my interest in studying the time fractional derivative is to generalize Brownian motion. This was my starting point. I want to see what happens when, instead of the first order time derivative, I take into account a fractional derivative in the sense of Caputo. And at the beginning it was a sort of joke. Let us see what happens. I have no physical reason behind this, just to see what happens when you replace the usual derivatives with the fractional derivatives. And the same thing was to see what happens when instead of the second order space derivative, I take into account the wreath fractional derivative. And I started also looking in the literature to see who was interested in these facts in the past. And I was surprised to see that in '51, a probabilist, which everybody knows, is certainly one of the most famous probabilists of the 20th century, William Feller, wrote a small paper where he generalized the wreath derivative. And his paper was published in an almost unknown journal. Really, it is some journal, local journal in Sweden. Don't know why. Because from my point of view, it was very interesting, first of all, that a person like Feller got some interest in these things. And it was strange that he published it in an unknown journal, and nobody looked at that paper. Weiss, in '86, wrote the explicit solution of the time fractional diffusion equation in a very strange way, involving new functions which were not so popular among probabilists, the Mittag-Leffler function and the right function. And this was what was known when I started getting interested in this fact. Francesco Mainardi told me that he made a lot of things in this area. He collected papers and tried to diffuse this idea as much as possible. And I did the same thing during recent years, above all in Russia. But Russia was the country where the first paper, the first book on fractional calculus appeared. In Russia, everybody knew that book, and everything of mathematics was studied. For example, in Russia, Brownian motion on non-Euclidean spaces was first introduced. and many other things, the existence of which I disregarded till recently, were known, and many people worked on them. So I have a great opinion about the Soviet and the Russian mathematics and probability. So, and my contribution in this area was to study what happens when instead of one fractional derivative you have more than one fractional derivative. For example, a fractional derivative of this kind plus 2 lambda derivative of order T alpha U equal to the second order derivative. This is a sort of time fractional telegraph equation. I was always interested in telegraph processes and motions at finite velocity related to this type of equations. So it was natural for me to see what happens if I take into account generalization in the fractional sense of the usual fractional equations, of the telegraph equations. So this was the first thing I did when I started being interested in this area. But in order to give a presentation which can be better appreciated, I start with a fractional equation where only time fractional derivative in the sense of Jefferson Caputo of X. So I take into account this diffusion equation, and consider the initial value problem where x at time 0 we have a delta Dirac function when nu is in 0, 1, and when nu is in 1, 2, you add another initial condition in the form of first order derivative at time t equals 0. This means t equals 0. And as I said before, if you consider here the Riemann-Liouville fractional derivative, you should consider initial conditions in the form of fractional derivatives. Instead, if you use the Caputo, Gerbaschan-Caputo derivative, you simply can use initial conditions in the form of integer order derivatives. And this is better because it is simpler to interpret the initial conditions. So for those who are acquainted with probability, it is a problem which is natural for those who are interested in Brownian motion. Instead of the heat equation, you have a fractional derivative here, and in a certain sense, when nu coincides with 1, the solutions must coincide with the Gaussian distribution, the transition function of Brownian motion. When nu is different, we must see what happens. And a lot of things happen when nu is different from 1. When nu less than 1 and nu bigger than 1. And the two solutions, by the way, I just give this picture because it is interesting to understand that when nu is equal to 1, you have the heat equation, and the fundamental solution of this equation is the Gaussian distribution. When nu is equal to 2, you have the D'Alembert equation, and the solution of this is the D'Alembert solution of the wave equation. But when nu is less than 1, the solution has this form. we will discover by means of the calculations that the solution, when nu is less than 1, has a structure which has one maximum, exactly as in the Gaussian case. Not differentiable here, it's symmetric, of course, because of the presence of the second order derivative. But when nu is greater than 1 and less than 2, you have something which recalls the structure of the D'Alembert solution. Something of this form, with two maxima, which move as time passes in this direction. Exactly what happens with the D'Alembert solution of the wave equation. How to express these solutions? We need new functions, not so new, but new for specialists of non-fractional calculus. The Mittag-Leffler function and the right function. The Mittag-Leffler function was introduced in the beginning of the 20th century. The right function was introduced in the 30s, as far as I know. And all the mathematics we introduced so far permits us to arrive to the explicit solution of this problem. The first operation to do is to consider the time Laplace transform with respect to t. Nu 0, 2, including 2, if you want. Initial conditions represented by a source Dirac function, which from the probabilistic point of view is the initial mass of probability at point x, at x equals 0, and this condition. Then you take the Laplace transform with respect to t, and the Fourier transform with respect to x. You pass first by taking the Fourier transform to this equation, U, say, beta of t is the Fourier transform, E beta of x, U x of t, the x, and you pass from this problem to the following one. Derivative of order U, t nu, minus lambda square beta square U, using this condition, of course, the boundary conditions that the solution must vanish as x goes to plus and minus infinite, and U beta 0 is the Fourier transform of the delta Dirac function 1, and ut beta 0 is equal to 0. Then you must take the Laplace transform of the fractional derivative of the Fourier transform. And we use the formulas I have just illustrated for the Laplace transform of the Gershon Caputo fractional derivative. And we have that the result, Laplace transform of the Fourier transform after some calculations, U x of t, the x is equal to s to the power nu minus 1 divided by s nu plus lambda square beta square. This is simply the application of Fourier transform with respect to space and the Laplace transform of the fractional derivative in the sense of Gershon Caputo. The problem is how to invert this. and at these points arises the necessity of considering new functions, in particular the Mittag-Leffler function. Mittag-Leffler function by the way, there are many types of Mittag-Leffler function, but the simplest one is defined as follows: E alpha beta of x is equal to x to the power k gamma alpha k plus beta. Alpha and beta for us are positive, x is a real number, k from 0 to infinite. Usually the Mittag-Leffler function is considered as the extension of the exponential. If alpha is equal to 1 and beta is equal to 1, you have the expansion of the E1 of x is equal to sum x to k factorial from 0 to infinite is equal to e to the power x. So many people speak of the Mittag-Leffler function as the natural extension of the exponential. And working on alpha and beta, you have many different forms. In particular, the problem which arose and was partially solved by Pollard is that when alpha is in 0, 1 and beta is equal to 1, E alpha 1 of x is a decreasing function of x. And so has the same behavior of the exponential. For this reason, many people consider probability distributions of the form of the Mittag-Leffler function because they look like the exponential distribution. And in particular, the following formula is well known: lambda t to the power alpha equal to sin alpha p divided by p integral from 0 to infinite e to the power lambda 1 over alpha w to alpha plus alpha plus cos p alpha plus 1 and w alpha minus 1 w. This is very important because it permits to express, yes, there is also t here, to express the Mittag-Leffler function when alpha is in 0, 1 in terms of the so-called Lamperti distribution. The Lamperti distribution is the distribution of the ratio of two stable subordinators. And so you have a contact between the Mittag-Leffler function and a well-known distribution of probability. But going back to what I was considering, we arrived at the double transform, time transform, and the Fourier transform with respect to x, and we have seen that the integral from 0 to infinite e s of t dt, integral from minus infinite to plus infinite e beta of x u xt dx is equal to s nu minus 1 s nu plus lambda square beta square. So the first step in order to arrive at the explicit solution of the initial value problem for the time fractional diffusion equation is to make the inverse Laplace transform with respect to time. And the inverse Laplace transform is the Fourier transform of the solution, has the following structure: integral from minus infinite to plus infinite e beta x.
Where does the mu come from?
Where?
Where does the mu come from?
From the equation, the initial equation.
So U is a solution of the
U is the solution of the initial value problem for this equation. U, the nu equal lambda square, second order derivative. This nu transfers to the double transform. And then, of course, if we make the inverse, no, it is the inverse with respect to time gives the Fourier transform of the solution, which must be written as a Mittag-Leffler function e nu 1 minus lambda square beta square t to the power nu. Very simple. Simply, the Fourier transform must be expressed in terms of one parameter Mittag-Leffler function. And to make a small check, if nu is equal to 1, we saw before that this is the exponential. So this becomes e to the power lambda square beta square t. This is the characteristic function of the Gaussian distribution, where the variance is equal to lambda square t multiplied by 2. So this is a check that shows that in the special case where nu is equal to 1, this coincides with the characteristic function of the transition function of Brownian motion. When nu is equal to 2, we must obtain something which recalls the D'Alembert solution of the wave equation, and it is exactly what happens. In particular, I can say not only that the characteristic function when nu is equal to 1 is this, but it is easy to give also the explicit solution in terms of Gaussian distribution. So U1xt is equal to e to the power x to the square, then 2 lambda square t divided by 2p, 2 lambda square t positive, and x is an arbitrary real number. This is the explicit solution when nu is equal to 1. Usually lambda square is equal to 1/2 in the standard Brownian motion. So you recover the usual formulas of standard Brownian motion. When nu is equal to 2, then you have that the characteristic function, the solution is e2 minus lambda square beta square t square. And e2 minus x square is simply cosine of x. So this can be written as e lambda t beta plus e minus e lambda t beta divided by 2. You take now the inverse of the Fourier transform and you arrive at the D'Alembert solution of the wave equation in the form of 2 Dirac impulses, U2, 1, or 2 x of t is equal to 1/2 delta x minus lambda t plus delta x plus lambda t. So as you have seen, I told you that when nu is in the interval from 1 to 2, the solution has this structure. And when nu approaches to 2, these 2 maxima concentrates and you take the form of 2 Dirac functions which move with velocity lambda in these 2 directions, in opposite directions. Now, in order to arrive at the explicit solution, you need to do some calculations. In particular, you need the representation of the inverse of the gamma function as a contour integral of this form. This is the Hankel contour e to the t minus z dt. Of course, the inverse gamma function has also this alternative representation as infinite product, E gamma z product of n minus from 1 to infinite, 1 plus z divided by n, E minus z divided by n, and gamma is the so-called Mascheroni-Eulero constant, which is approximately equal to 5, 7, and is equal to the limit of 1 plus 1/2 plus 1 of n minus log of n. But in our context, we need this representation of the gamma function because the derivatives involves the gamma function, and we must work on this gamma function. In particular, the Mittag-Leffler function with parameters nu gamma of x is equal to the sum k divided by gamma nu k plus gamma, gamma from 0 to infinite, and for us nu is positive, gamma is positive. The inverse of the gamma function can be written in terms of contour integral as follows. No, I have not written it here because I only wrote the right function in explicit form. But you can simply replace the inverse of the gamma function, make some calculations, and you arrive to the contour integral representing the Mittag-Leffler function. By the way, the Mittag-Leffler function, as I told you, has these specific values: e of x equal to x, e to 1 of minus x squared is equal to cosine of x, e to 1 plus x squared is hyperbolic cosine of x, cosine of x. A check that we are on the right way is to make the Laplace transform of the Mittag-Leffler function, that is e to the power s of t of nu 1 lambda square beta square t of nu in the t. And if you make this calculation accurately, you arrive at the formula s to the power nu minus 1 divided by s nu plus lambda square beta square. So this is a check that the inverse Laplace transform of this function is exactly the Mittag-Leffler function. This is a check which doesn't take much effort, and you simply can do it rapidly. Now, as I said now, the subsequent step is to invert with respect to space. Inverting with respect to space, you need a new function, which is the right function. Right function. Which is regarded as an extension of the Bessel function. W alpha beta of x is equal to sum x to the power k divided by k factorial gamma alpha k plus beta, k from 0 to infinite. This is the definition of the right function, and here we need that alpha is bigger than -1, beta is positive, and x is a real value. Why? Oh, excuse me.
No, don't worry. Few minutes otherwise.
No, I didn't realize that it is already 2 o'clock, 1 o'clock. So I stop here because I have presented many more results than I expected, because I have not given the proofs of most of the results I presented in the first part of the talk.